welcome. One of the nice things about calculus is that we get into some of the really big and important ideas of the class right away. So, today we'll be talking about tangent lines, and we'll be getting into derivatives right on the first day. And I wanted to motivate this with a really old problem. So this handsome fella on the left here, this guy, that is a guy named Zeno. Cool name. He was from ancient Greece. He was born about 2,500 years ago, and he was thinking about some problems that he was definitely not the first to think about, but he really took the time to bring them up to try to prove some people wrong, and they got written down, and so now we know them as Zenos Paradoxes. There are a number of them. So one of the most famous, and one of the ones we're going to care about, looks a little bit like this. Say Zeno here shot this arrow, and it went to the target, and he was a great shot. Well, Zeno was really concerned about time and motion and the way we were thinking about it. So he said, hey, on that path, that arrow was in a whole bunch of locations. And at each of those locations along the way, it was taking up one spot in space. And in that one spot in space, it couldn't have been moving. And so if at every single spot along the way it wasn't moving, then the whole time it wasn't moving. And so the arrow couldn't have gotten anywhere. And yet we saw it fly across the screen. So how is this possible? He had his own kind of things he was trying to disprove, and clearly there's something wrong here. It was one of several big thoughts that had to do, when you break it down into notions of infinities and infinitesimals, right? What happens when we break things into infinitely small pieces? A lot of our intuitions start to break away, and a lot of the math we use starts to fall apart. So, to take the next step in making this a little bit more relatable, we might consider something like me here on the left, running. Those are motion lines on the left, so I might be running to a finish line. And if we wanted to talk about how fast I ran along the way, well then, what we would normally do is talk about how far did I go and how long did it take. So, I might even have a little chart like this, and on that chart, maybe at time 0, I had gone 0 feet. And after, say, 1 second, maybe I had gone 2 feet. And after 2 seconds, I had gone 5 feet. And after 3 seconds, I had gone 10 feet. And then I started to get tired after a whopping 4 seconds. Oops. And so maybe I only get, say, 11 feet. Oops. Messed up again. And then I make a real big push in those last two, and I get, say, 13 and 15 feet. Okay, so this is my 6 second, 15-foot race. I teach math, so I don't have a whole lot of endurance. Well, we might ask, how fast did I go? Okay. In other words, what is my average velocity? And I should point out, actually, before I go there, that a lot of times we'll write these tables vertically. We'll see this a bit. So often we'll write them more like this: 0, 1, 2, 3, 4, and so forth. And we'll write 0, 2, 5, 10, 11, and so forth. So don't be shocked if you see this in a vertical table instead of a horizontal one in the future, just depending on preference and whim. Okay, so let's say we want to talk about how fast we're going. Often we'll talk about velocity, which has a direction. Velocity can be negative, whereas speed can't be negative. So a negative velocity just means you're going backwards. But we could answer this question: what is my average velocity from t equals 1 after 1 second to t equals 4? And there is a natural way to think about this. It is how far did I go divided by how long it took. So how far over how long it took. Okay, just kind of informally. Well, what does this look like? How far did I go? Well, in the end, at t equals 4, I was at 11. But I didn't start at 0. I started at t equals 1, so that would be 2. Okay, so I went 11 minus 2, and it took me, well, I ended at 4 seconds, but I started at 1, so it took me 3 seconds. In other words, this is going to be 9 over 3, also known as 3, and if we want to include units here, I believe I was saying this was feet per second. Okay, and that's often how we talk about average velocity or average rate of change. And we could do something similar. This might not be very satisfying if I'm really trying to figure out how fast was I going at 1 second. It might be a little closer to say, hey, on average, how fast was I going in between t equals 1 and 2? And once we've done this once, we can do it pretty fast the second time. At t equals 2, it looks like I was at 5. At t equals 1, it looks like I was at 2. And how long did that take? I ended at 2 minus the one I started with. So this would be 3 over 1, and by sheer coincidence, this is also equal to 3 feet per second. Okay, a couple of things I want to point out here. One is that we wrote this a little differently from here to here. T equals 1 to t equals 4 versus t equals 1 to t equals 2. This is our interval notation. Notice these square brackets are saying include the 1 and the 2, so it's not uncommon to see it this way. And I'll be doing a lot of this just from one example to the next, trying to write things in different notation to make sure that we are exposed to lots of different notation. T equals 1 to t equals 4 is a little bit more like writing it in English. Okay. Second is that it actually doesn't matter if I were to reverse the order of these, as long as I'm consistent. Okay, as long as that this 5 and 2, right, at t equals 2, I had a distance of 5. As long as those both come first or both come second, it really doesn't matter, because under the hood is something called slope, which we'll be seeing in a second. Okay, but hopefully this is a nice intuition that when we're talking about velocity, we're talking about the change in distance on top divided by how long did it take, right? It's some description of this relationship between distance and time, just like Zeno was talking about. The big interesting question is, what is this instantaneous velocity at t equals 1? Meaning, how fast am I going at that exact second? And we could try, maybe I'll put this in red, just to try to do this. Well, at t equals 1, it looks like I am at 2. And I'm still at t equals 1, so I'm going to subtract 2. And then I'm going to divide, do a little slanty divide here. At t equals 1, I'm at 1 minus 1. And this is 0 over 0. That's worth asking yourself, what is 0 over 0? And if you had any impulse to say 0, I need you to go ahead and wash that from your brain right now. 0 over 0 is undefined. I don't care what's on top. When there's a 0 on the bottom, I don't know what this is. It's not 1, it's not 0. I really just don't know. And this is this big problem. When I want to talk about how fast am I going right now, we've got this intuitive sense that at any given moment, I have some speed. At any given moment in time, I have some speed. But when I stop to measure it at a given moment in time, well, I don't have a denominator anymore. I don't have a change in time at one moment in time, and this is what Zeno is getting to. And this is particularly maybe confusing if you're used to looking at your car telling you exactly how fast you're going at any moment in time. That seems to be this very continuous thing, that you always know how fast you're going at that moment. But this basic idea of how far divided by how long really doesn't work anymore if I want to talk about an instant in time, just as Zeno was trying to point out hundreds of years ago. He wasn't even the first to really realize that this was a problem. Okay, so the question for us, this real big question for us is, what on earth are we going to do with this undefined thing? Oops. Okay, we want to make sense of this because we have some intuition that says, yes, we are moving. There should be a number there for how fast we're moving. but this math is breaking down and our intuition is breaking down. And that basic notion of what is a rate of change at an instant, that is the heart of calculus, right? At least for us right now. And dealing with this 0 over 0 issue is going to take us into a world of limits, which is going to be a big part of this class as well. And how do we talk about those infinities and infinitesimals, I think is pretty exciting.